Teacher Carlos Plain of Durham School states definitively, "I went through my entire time on Earth empowering a specific hypothesis of the universe. Also, eventually, the hypothesis is being attempted. I welcome that, since that is how we push ahead. That is how we make progress in science." The James Webb Space Telescope is upsetting an incredible arrangement of what has been seen as truth in cosmology for the new years. Another ultra-deep image shows that we have serious goofs in cosmology. The telescope that should show us the fundamental stars of the universe is changing into an enemy of the previous perspective and may present to us a completely remarkable science. Not all agents are groveling in dread at the new realities. Other subject matter experts welcome the developments, since it has for quite a long time been certain that something was the matter with our old speculations. The deviation in the appraisal of the development speed of the universe alone should have shaken specialists' perception at some point in the past, yet taking everything into account, they stuck to old speculations. The cosmic microwave background radiation, CMB, considered the most settled light in the universe, was made around 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to form stable hydrogen particles. Scientists call this process reionization, which made the universe transparent to light. The CMB was first seen in 1964 by American physicists Arno Penzias and Robert Wilson while they were dealing with another type of radio-receiving wire technology. This discovery was for a long time seen as possibly the strongest piece of proof for the theory of the prehistoric cosmic detonation, earning Penzias and Wilson a Nobel Prize and an obvious spot in the history of astronomy. The CMB probably offers a view of the early universe, with small temperature differences giving critical data about the conditions not long after the Big Bang. Researchers involved the CMB as a solid scraping of the crucial assessments of the material universe to check the development speed of the universe, among other things. The cosmologist Edwin Hubble had previously settled this in the late 1920s, finding that distant galaxies retreat from us, and that their speed is proportional to their distance. Today, these observations are known as the Hubble law or the Hubble constant. Hubble didn't have the high-level evaluating procedures available many years later when the CMB was found, which prompted a recalculated expansion rate. These were generally lower than Hubble's original figure. Later, researchers recalculated the rate once more using type Ia supernovae as standard candles, providing stable light that could be used as a dependable measuring point. The estimates within the CMB yielded an expansion speed of around 67 kilometers per second per megaparsec, while estimates using supernovae yielded around 74 kilometers per second per megaparsec. What does this discrepancy in determining the expansion speed of the universe truly tell us? Did you understand that this goof has been known since the 1990s? Since then, analysts have known, or at least suspected, that something may be the matter with the assessment of the CMB, the estimation procedures, or the prospect of the universe's expansion. The anomaly between the observed and expected values of the expansion rate is referred to in science as the SAA pressure or Hubble strain. The ramifications of this strain are gigantic, showing that basic parts of how we understand the universe may be flawed. For years, specialists were puzzled. Since the James Webb Space Telescope went into operation, it has provided experts with astounding information that may now reveal data on the issue of the expansion speed of the universe, with systems so old and mature that their evolution should have begun theoretically before the Big Bang, toppling old cosmology. Scientists no longer discuss mistakes or estimation differences. They discuss the greatest emergency in current astronomy. Not only could the expansion rate be off track, but the entire idea of progression or the Big Bang itself is being called into question. Images from the telescope give proof of a universe totally different from what we have long thought. The SAA pressure was the first reproach to specialists, who still have faith in old theories. Now they face a problem. Do we truly understand the universe? Other researchers stand on the remains of their once wonderful source of both discovery and torment, analyzing space with fear and wrestling with what they find, considering the emergency in science. We should ask ourselves, what do we truly know about the universe? To answer this, we need to understand how science functions. Hypothetical researchers utilize a complex set of mathematical models, careful data, and logical reasoning to move conclusions from the general to the specific. Their understanding comes from a blend of observation, characteristics, fundamental results, and speculative estimates. The term theory alone shows that these are constructs and ideas, not absolute pieces of knowledge. The only actionable data we have are the photographs telescopes provide, the sound waves and radiation collected with radio telescopes, and the latest data from neutrino surveying systems or gravitational wave detectors. With the James Webb Space Telescope, we now have an instrument that can split the light into individual frequencies and analyze it in extraordinary ways. Webb can show us the fundamental components of galaxies in the early universe, in excess of 13 billion years ago, the amount of mass they contained, and how many stars were present. It can also track the shape and course of a galaxy's evolution. Webb can, however, have limitations. For instance, it can't always definitively determine whether we are seeing galaxies or black holes with massive gravitational pull that radiate as brightly as a galaxy. We must face the truth that our science has long accepted an excessive number of possible outcomes as facts, while dismissing alternative explanations. Research has for decades been confident in its accuracy. The latest discoveries from the James Webb Space Telescope are crucial hints to replace theories with new insights, as has happened historically in science. Researchers are eagerly awaiting the new discoveries, which are unexpectedly astounding, and other specialists are struggling to develop new explanations. The new revelations shake the foundations of our current science, disturbing many specialists. The current models of real science are still largely based on Isaac Newton's laws from the 17th century. His laws of motion and gravity were the foundation of our understanding of the reality of this world and the universe for many years. Newton's rules explain the motion of things under normal conditions and function extraordinarily on Earth. However, in space, his theories required development, largely completed by Albert Einstein in the early 20th century. Einstein's special theory of relativity, published in 1905, changed how we interpret reality, showing that time and space are relative to each other and depend on the observer's motion. His general theory of relativity, published in 1915, extended this idea with mathematical assertions of gravitational characteristics based on the curvature of spacetime by masses like stars or galaxies. Einstein's rules and ideas were astute in various areas. However, he also understood their limits. He knew his theory could never absolutely describe the universe and longed to see a unified theory, which he never achieved. No other trained professional has reached this stage either. Wouldn't it be fascinating to know where it lies? Michio Kaku, a prominent astrophysicist from the USA, said in an interview that solving this issue would certainly win a Nobel Prize. Could we explore whether the experts may have missed possible misinterpretations or whether our telescopes are to blame? Dark matter and dark energy are at the top of the suspect list for the underlying causes of the cosmological emergency. Our evolving models of the universe combine concepts that dark matter and dark energy make up around 95% of the universe. However, neither has been clearly observed, and their confirmed presence has never been demonstrated. They might not exist in any form or shape, requiring alternative explanations for the universe's expansion and the dynamics of galaxies. Alternatively, they could have properties we don't yet understand. One thought is that the true properties of dark matter and dark energy have changed over time, potentially showing some form of evolution. Gravity is another theory to be tested. This force, which induces interest through mass or curvature in spacetime, has not yet been fully explained. The ideas of spacetime curvature, which originate from Einstein and have been supported traditionally, may need revisiting. We cannot dismiss the possibility that gravity has unexpected properties, or that another force is responsible for the gravitational attraction between objects over time. A few constants have been established in cosmology and astronomy as universal principles. The study of the universe has always been a journey defined by our relentless quest for understanding and discovery. From ancient human civilizations observing the stars to modern space telescopes probing the depths of the universe. Every advancement in development and theory has uncovered new secrets while testing established beliefs. In the field of cosmology, the James Webb Space Telescope, JWST, remains as a beacon of our scientific progress, promising to transform how we interpret the universe's origins and evolution. Launched with exceptional capabilities, JWST represents a leap forward in observational space science, designed to look further into the universe than any time in recent memory, with unmatched accuracy in studying radiation. The CMB, often referred to as the glow of the Big Bang, offers a view of the universe as it existed just 380,000 years after its first encounter with the world. This ancient form of radiation carries critical information about the universe's early conditions, including its temperature variations, which are key to understanding the evolution of galaxies and large-scale structures. The discrepancy in the calculated potential values of the Hubble constant, known as the Hubble tension, has been a topic of extended debate. It suggests that something is wrong with our fundamental understanding of the universe and its beginning. Webb's revelations challenge conventional theories and demand a reevaluation of whether our perspective on cosmic evolution is fundamentally flawed. New insights may reveal hidden aspects of the universe's creation, raising questions about dark matter and dark energy, two unexplained components that make up most of reality. The advancement of science relies on the ability to reshape our theories based on new data. Webb's mission embodies this pursuit. Its discoveries will serve as a foundation for future cosmological discussions and should spark new perspectives on the universe's mysteries. The future of cosmology may witness significant changes, leading to profound implications for our understanding of the universe, from the Big Bang to the ongoing cycles that define its fate. The answer to the great cosmic riddle may lie beyond our current knowledge, and Webb's observations may ultimately be crucial in uncovering new insights that could reshape how we interpret reality itself.